Hello everyone, welcome to the third lecture of this course. In the previous lecture, we discussed the syntax of lambda calculus and some problems related to syntactically correct lambda terms. Today we are going to discuss free variables, bound variables, scopes, beta reduction, alpha renaming, eta conversion and some computation examples. First we are going to discuss the motivation of free variables. Free variables we have already seen in different forms at different places. For example, integral calculus, when we have done summation, in first order logic, in programming that we have done. So we are going to touch upon one by one each of them. So consider first integral calculus. So here we have a definite integral which reads as x plus y dx. So here x is the integration variable. So when we integrate it, we will get a function of x and y. Now the x will be consumed by the limits of the integration 0 and 1. So we will left with some constant value together with y. That y can take on any values. So hence y is a free variable and x is bound by the integration variable dx. Next we have summation. So here we can see it is a summation of I is equal to 1 to n and we do I plus k. So here I is the bound, that is a summation index, whereas k and n they are free. K and n means they can take on any values, but I is bound in the sense that I will take on values to 1 to n. Next we have first order logic. So first order logic sentence we have, for all x, px implies qy. Now here x, the variable x is bound due to the universal quantifier for all x, whereas y, there is no corresponding quantifier with respect to y. So hence we call y free and x bound. Let us now see some C programs. So the first program we have declaration like int z is equal to 10, which is a global variable, z is a global variable, and you have a function where the parameter int x is the parameter and it is returning x plus z. So inside this function x is bound whereas z is free. Now let us see the other program where we have int z is equal to 10 and it is returning x plus z and the parameter is x. So both x and z in this case are bound. There are no free variables here. Now let us see some examples from linear algebra. So first one, we have two equations with two unknowns. So the first equation is x plus y is equal to 2 and the second equation is 2x plus 3y is equal to 5. So if we solve them, we will get unique values of x and y, that is 1. So we say that both x and y are bound, that is their values are fixed by the system. So there are no free variables in this case. Now let us see the next example where we have one equation with two unknowns. So the equation is x plus y is equal to 2. So the solution is x is equal to 2 minus y, or we can write the other way also, y is equal to 2 minus x. So let us see x is equal to 2 minus y. Here x is dependent on y. That means y can take any values and value of x will be determined by the value of y. So hence y is free, x is dependent. Now let us see the intuitive idea of free variables. A variable is free if it isn't captured by a nearby lambda. So here in that first order logic expression, that x was captured by the for all quantifier. Same happens in lambda term. So here lambda x dot x, this x is captured by the nearby lambda. So that means x is not free here. Moving on to case 2, you have lambda x dot xy. As before, x is captured by this lambda, but y is not captured by any nearby lambda. Hence here y is free, x is not free. Case 3, now we have lambda x dot y. Now we know that y is free because there is no nearby lambda to capture it. But what about x? Here x does not occur in the body, in this body x does not occur. However, lambda x makes x bound in P. So here x is a bound variable, y is free. This is an important point to note. Lambda x means x will be bound. Y we have to see, the other variables we have to see whether there is a nearby lambda. So whenever we have lambda x, lambda y, that whether it occurs or not, it will be bound. Other things we have to see whether they are bound or free. So then we can formally define the free variables as, So we take three cases. We know that there are three constructs in lambda calculus. One is the variable, another is abstraction, another is application. So free variable will be a set of variables that we are going to get. So first one is free variable of x is a singleton x. Free variable of abstraction, that lambda x dot m, it is a free variables of m. Set difference, this is a set difference singleton x. That means free variables of m excluding x. And application mn, free variable mn is a union of free variables of m and union of free variables of n. Now let us work out the examples that we have discussed informally. So free variable of lambda x dot x. So this is x is the body. So it will be free variable of x excluding x. So that will be free variable x is x set difference x is empty. So there is no free variable in this example, lambda x dot x. Now free variable of lambda x dot xy, we know y is a free variable. So let us compute it as per this definition. So we have free variable of xy, set difference x. So free variable xy will be free variable of x union free variable of y. That is, free variable x is x, free variable of y is y. So set difference, it will be x union y minus x, it will be y. So we have got the free variable of this lambda term is y. Now consider example 3. We have lambda x dot lambda y dot xz. So we know the answer. We know that because of bound thing, the xy will be bound. So z is not captured, so z will be free. So let us verify this according to our definition. So let us see lambda x dot lambda y dot xz will be lambda y dot xz set difference x. So let us compute this part first. So this will be free variable of xz set difference y. So this is free variable of x union free variable of z set difference y, that is xz set difference y will give us xz. Then we substitute here. So we get lambda x lambda y xz is xz set difference x is z, and this is what was expected, and we have got this result by using the definition of free variables. In the like manner, we can discuss also about bound variables. So the bound variables definition would be very similar. So now we know that again we have to consider three cases. The bound variable of x, that means x is free, so that means it is not bound. So that means we write it is an empty set. Now bound variable of lambda x dot m is bound x will be bound, so we have to do union of x. So bound variable of m union the singleton x. Bound variable of mn will be bound variable of m union bound variable of n. Now let us work out this example, lambda x dot lambda y xz. So here we see that z is free, x and y are bound. So the bound variable answer we know intuitively is x and y. Let us work out according to this definition. So bound variable of xz, let us do this first. So bound variable x union bound variable of z, that will be empty set union empty set is empty set. Then lambda y dot xz bound variable, we are doing bound variable of lambda y dot xz, that is bound variable of xz union y. So that is empty set union this set containing only y, it is y. Then the bound variable of the entire term, that is lambda x dot lambda y dot xz, is bound variable of lambda y dot xz union x, that is y union x, that is xy. So indeed we have got the result that we were expecting. Now let us discuss scopes. The scope of a variable is up to the rightmost part possible. So we underline the rightmost part possible. It is not rightmost, to the right we will go, but to the extent possible. So we will explain this. So consider this lambda x dot lambda y dot c. So first y scope is to the rightmost part possible. Here it is up to this. X scope is up to this possible. So this is the scope. Y goes to the right as much as possible. As much as possible is this. Here x is as much as possible here. Here the scope of the variable x is up to the last occurrence of x, and y is also this one. It is this body, it will be covered. There could be another y as well. So it will be that scope. Now consider lambda x dot lambda y x dot yx. Now you have to see rightmost part possible. Now x again if I do like this, whether it will be I can go to the rightmost part or not, we have to see. So one is I will go, but I see there is again lambda x here. So what should I do now? So here the scope of the variable colored red is not up to the last occurrence of x, because it is captured by the inner lambda x. So this x scope, blue one scope is up to this. So the scope of x is everywhere excluding the places where it is being captured. So now this rightmost x refers to this one. It is not referring to the x colored red. Y scope is as before. So we will say that here in this term, that x that we are having in the body refers to this blue x and not to the x colored red. So we can rename this blue x as z. So to avoid any confusion, we have lambda z dot yz. This is lambda y this. Now you have x scope as before. It is to the right as possible. Y is this one possible. Z is this one possible. So we have no problem at all. So we illustrate, we see that there is a very close similarity about scopes in programming languages as well. So consider the C program. So here let us see this function, that is int foo, int x. So this x here it is a parameter to this function. So we say y is assigned the value x. So here we are printing y. So this y that will be printed will be this value of x will be printed here. We know this. Now what we do here, we have a for loop, and here I is equal to 1 less than 2. That means the for loop will go only once. Now here we write int x, that means it is a redeclaration. That means this x is not the outer x that colored red. This is different. So here what will happen, as if it is a new x, so that means int x plus 1, it will be 0 plus 1. So this will be 1, and y will be here 1, because y is within the scope here. This scope is, so there are nested, one is this scope and the outer scope is this one. So y value will be 1. So now y returned value is 1. So here result printed will be 1. So this will be printed 1. And here first time when we passed to 5, so it printed 5 here. Now if we remove this one, this int, that means this x is this x, red x. So this will be 5 plus 1, this will be 6. So then the output will be 6. So here the correspondence between this and the lambda term is this lambda x, that is this int x. This x is visible everywhere unless it is occluded or it is shadowed by a redeclaration. So here we can think of this part as a redeclaration which makes it shadowed. This x is, that means this x shadows the outer one. So which is tantamount to saying that okay, this x I can make very well as z, int z. Int z if I write, here also we write int z, so it is the same thing. So this is the idea about scopes. Now we talk about beta reduction. So we know in lambda calculus is essence is a term rewriting system. That means we start with a term and we do a reduction which is called beta reduction, and we get another term. So how this beta reduction happens, formally we have to discuss this. So we have a term like lambda x dot m, and n is lambda x dot m is a function, so it is applied to n. So when we do beta reduction, it means in the body of m, all free occurrences of x in m will be replaced with n. So this is very important. In the body of, in this m, we look for all free occurrences of x, and all free occurrences of x in m will be replaced with n. So the notation here is, so this notation is to be read as in the body of m. This square bracket says in the body of m, all free occurrences of x, this n slash x means all free occurrences of x in the body of m will be replaced with n. This is the idea of beta reduction. Not one occurrence but all occurrences. So if x occurs 2 times, So both the places it will be replaced with n. So if you have lambda x dot xx and you have n, so beta reduction will give us nn. There are two free occurrences, 1 and 2, both are replaced by this n. So this is the idea. So we will take several examples to illustrate this idea. So first is m is here lambda x dot m is here x. So the x is here in this body, x is free. So it is free, so we can replace this with n. So if you get this, we will obtain lambda x dot x. So here once again this is m, x is free. So all free occurrences are, only one occurrence is there. So this occurrence will be replaced by n. This is our n, this is our n. So we are replacing this x in body m with n. So we are getting lambda x dot x. Now here you have lambda, we have lambda x dot y and this is n. Now something interesting is happening here. This body is y. We don't have any occurrence of x at all. We don't have any occurrence of all free occurrences of x to be replaced with n. But now there is no occurrence of x at all. What we are going to do? So then no replacement is possible. So that means the answer should be y. No replacement. If no replacement is possible, then we keep it as it is. So it means that if there are any free occurrences of, if there is any free occurrence of x in the body, that will be replaced by n. That was the idea. So there, since there is no free occurrence, it will be untouched. It will be keeping as it is. That means this term, entire term reduces to y. Now why it is like this? So we need to understand it intuitively. So what lambda x dot y says, it is a function. So it is a function with input y. The input is x, sorry, and it is giving y. That means irrespective of this input x, we are doing y. So it is a constant function which does not depend on the input. So that means whatever parameter we pass now for x, whatever might be n, answer will always be y. So that is why lambda x dot y n beta reduces to y for any n. So this is an important term, we should keep it in mind. So whenever we have this sort of a term, we will reduce it to replace this one with y. Next is alpha renaming. Alpha renaming is a way of renaming variables. So for example, we have integral fx dx. We can rename x, all occurrences of x here with y. These two things are same. Fx dx integration is the same as fi dy. Now here for example, let m is equal to lambda x dot x. Here x color is red, we have written. Another n, this is the n part, is y. So this obviously we know that this x, these scopes, we know that these two x are different. So then we can change this to make it distinct. We can change one of them to say something y. So we have changed this blue one to y. So lambda x dot x, lambda y dot y. So this is by alpha renaming we have obtained this. There is no change in the meaning at all. Now when can we do this? This is what we want to discuss. Now consider the example that we have discussed earlier. So here we have this 2 lambda x, which is confusing, which may be confusing initially. To beginners it may be confusing. So we said that the inner x and the outer x, they are different. The idea is to have all argument names distinct. So we can say that okay, this x will change it to z and this will keep it like this. So now you have all parameters distinct. So there is no confusion at all. So this is alpha renaming. Now let us take another example. So we have lambda x dot yx. Now I wish to rename x as y. So okay, is it possible? So if I rename x with y, what am I going to get? I will get lambda y dot yy. Now let us examine these two terms m and p. Here in this p, y is not free. Here in this m, y is free. That means, this means these two things are different. P and m are different. So that means this thing that we have done is not allowed. So we want to express it formally. When we can do and when we cannot do. So alpha renaming, if x is bound in lambda x dot m, you can rename it to y as long as y does not occur free in m. That means lambda x dot m by alpha renaming it will become lambda y, this is the bound thing, x is the bound, so we make it, and all occurrences of x in M we change it to y, provided y is not a free variable in M. So in the previous example, we were trying to replace x with y, but y is a free variable here, so we cannot do that. So then you cannot replace x with y, but we can replace x with z. This example, lambda x dot xy dot xy, lambda x dot lambda y dot xy, here we can change y to say some v and x to u, it will be the same thing. So this is alpha renaming. So the idea about alpha renaming is to prevent variable capture, clarify expressions. Now there is another reduction strategy, so that is called eta conversion. So consider a lambda expression of the form lambda x dot mx, where x does not occur free in M, that means x is not part of the free variable of M. Then we wish to see what will this happen, lambda x dot mx, the rule says eta reduction, so this is called eta reduction, lambda x dot mx says we are going to get M. So let us examine this. So the idea is that let us say this is one function f and this is another function say g, this is our function f and g. So we know that if fx is equal to gx for all x, fx is equal to gx, then f is equal to g, this we know. So that means for all arguments, if these two functions behave in the same way, we call these two things as same. So then these two functions then by this rule says they should be same. So let us see why they are same. So we say lambda x dot, so we say M is lambda y dot y, then we have x, lambda y dot yx. This is our part left hand side f, and I supply it with u. So this is I am doing M of u, this f of u, I am doing f of u. So then what I will get by beta reduction, I know that it will be lambda y dot y of u. I am replacing this x with u. So again this we will going to get u. Now if I do g of u, then it will be lambda y dot y, g is M, this is u, this will be u. So both are yielding the same result. Both are yielding the same result. Hence we can change the structure lambda x dot mx to M. Now here one thing to be noted, that if M is not a lambda, M is a y, M is a y, then this term will not be reduced because it is a normal form. Sorry, we will have to discuss normal form, means this is already in a simplest way. So if you have yx, we have not discussed normal form, I should not use that word. So lambda y, you do it, nothing is going to happen. It will be lambda, same thing we are going to get. So that means this M is a kind of abstraction. It must be a form of abstraction. So if M is an abstraction, that is lambda y dot p, so mx will get rid of this lambda y and we obtain in the body of p all occurrences of y replaced with x. Now the new term will be lambda x dot in p, y replaced with x. Now you do alpha renaming. So this will yield us M. So the purpose of this eta conversion is that this term looks a little bit more complicated. We can get rid of this lambda because this x was used to get rid of this internal lambda. So we remove M and get M. So remove the abstract, redundant abstraction. Now that we have studied these three techniques, one is beta reduction, alpha renaming, eta reduction, you might think that why there are so many things like that. Are there anything else? No, there are nothing more. We have only these three. So let us give a look, revisit these things. So beta reduction is the heart of lambda calculus. That means this is the basic fundamental term rewriting rule. You have a term T1, it changes to T2. That is what beta reduction is going to do. A very restricted form of a structure, when you are supplied with a very restricted form of a structure, as we have seen, lambda x dot mx where x is not occurring free in M, then we are replacing it by n. So, it is a special kind of, we can say, specialized term rewriting. Alpha renaming, in contrast to beta and eta, they are quite different. Alpha renaming says that we are just renaming the bound variables, but that will not create any change in the meaning of the term. So, the structure of the term remains same. So, this is the idea about alpha, beta and eta renaming. So, once we are familiar with lambda terms, we may not do alpha renaming at all, because we are well conversed with these things. We know which x means which x and so on. So, that will be quite clear. We need not do alpha renaming later on. But if at any point of time you feel that you are not quite confident, so you do alpha renaming and then carry out with the term reductions as per your convenience. So, now we can see this some computation examples. These are standard combinators. Combinator is a lambda term that has no free variable. Combinator, these are standard. So, they are combinators come from combinatory logic, which predates lambda calculus, and these are some standards, the notation the people write k. So, these are if you look at the textbooks and combinatory logic, they use the notations. It was done by the logicians. They write k for first, second k star, I is identity and so on. You have other things like successor also, you have things like that. Later on we are going to see. So, simplest lambda term is the identity function. So, identity function is lambda x dot m. Whatever you put as input, you are going to get the same out. Lambda x dot m is m for any m. First mn is, that means you are saying that if you have supplied two arguments to first, I am always going to get the first argument. So, if you want to do that, you write a term like lambda x dot lambda y dot x. You supply two arguments, you get the first one. Same holds for, you want to get the second argument lambda x dot lambda y dot y, then it will get the second argument, you are going to get n. Now, this term let us examine. You have two arguments lambda f dot lambda x dot fx. Here x is a variable, f is applied, so f is a function. So, it is a higher order function. A higher order function is one that takes as input a function or returns an output as a function or both. So, that is a higher order function. So, twice, that means we are applying this function twice. So, we are doing f of x, it is again a higher order function. When we are doing composition of two functions, we are doing fx, then we are doing g of fx, it is also a higher order function. Now, see the interesting thing that we have studied in our school days, integration. Integration is, if you do integral of say sin x dx, we are going to get minus cosine x c. So, here the integral, the input to the integral is a function fx, output is again a function say gx. So, it is a mapping from one function to other. So, it is taking as input one function, returning as output. It is an example of a generalized higher order function. The same is true for differentiation. It takes as input a function and returns, because it is antiderivative. It is the reverse process of integration, or the reverse process of differentiation is integration. So, that we know. So, this is an example of higher order function. So, thus we can summarize today's discussions as we have given. Hope you have got some idea about free variables, bound variables, the scopes of lambda term, the different reduction strategies and the how this computation works. Thank you for your kind attention.